Good evening. I am the leader of Group 1 and our topic is composites. We formally start our report. Allow us to introduce ourselves first.
Hello everyone, my name is Joshua D. Kabatingan and my topic is what is composite.
My name is Ibi Marcosi Arcilia and my topic is where is composite used?
My name is Christian M. Busotros and my topics was advantages and disadvantages of composites material.
I am General Katantan and my topic is to investigate of what are the possible composite materials being used in the field of electronics engineering. In this generation, it is evident that devices or technologies are in demand due to trends and needs in various components. With the help of these creations, it helps people in making their tasks way easier. The growth of the electrical industry has provided an evolving market for electrical composite materials. As equipment gets more sophisticated and technology advances, the role of thermoset composites will continue to expand across industries and applications. The streamlining of composites manufacturing processes and the development of new manufacturing forms meet the demand for faster cycle times, make composites more cost-effective, and provide enhanced quality and lower processing costs.
What is composite? A composite is a mixture of two or more phase materials. A better or unique combination of properties is realized when different materials or phases are combined. The primary needs for all the advanced composites are higher operating temperatures and greater stiffness, higher reliability, and affordability. What makes a material a composite? A composite materials are formed by combining two or more materials that have quite different properties. The different materials work together to give the composite unique properties. But within the composite, you can easily tell the different materials apart. They do not dissolve or blend into each other. So why use composites? The greatest advantage of composite materials is a strength and stiffness combined with lightness by choosing an appropriate combination of reinforcement and matrix material. Manufacturers can produce properties that exactly fit the requirements for a particular structure for a particular purpose. Modern aviation, both military and civil, is a prime example. It will be much less efficient without composite. In fact, the demands made by that industry for materials that are both light and strong has been the main force driving the development of composite. It is common now to find wing intel, sections, propellers, and rotor blades from advanced composite, along with much of the internal structure and fitting. The airframes of some smaller aircraft are made entirely from composite, as are the wing, tail, and body panels of large commercial. I'm thinking about planes. It is worth remembering that composites are less likely than metals, such as aluminum, to break up completely under stress. A small crack in a piece of metal can spread very rapidly with very serious consequences, especially in the case of aircraft. The fibers in a composite act to block the widening of any small crack and to share the stress around. What are composites made of? Human learns from Mother Nature to develop new composite materials. Natural composites, wood and bamboo, shells, bones, muscle, other tissues, and natural fibers, silk, wool, cotton, jute, sisal. Composites are simply a combination of two or more constituent materials with different physical or chemical properties. When they combine, they produce a material with characteristics different from their original properties. The two main components within a composite are the matrix and fiber. The matrix is the base material while the fiber is what reinforces the material. On top of the fiber reinforcement and matrix composites can also include core materials, fillers, and surface finish to provide unique performance attributes. So for the four types of composite, particulate reinforced composites are composed of hard particular constituents which are scattered in a softer matrix in an arbitrary manner. Number two, flake composite. This type of composite is produced by blending matrix material and then flakes. Number three, fiber reinforced composite. Fibrous composite. It is a composed of a strong and stiff fibers which are held together by a matrix. Number four, laminated composites. Laminated composites are made from completely bond then elementary layers.
Composite materials. A composite material is a material which is produced from two or more constituent materials. These constituent materials have notably dissimilar chemical or physical properties and merge to create a material with properties unlike the individual elements. Composites are ideal for applications in corrosive environments such as chemical processing plants, pulp and paper converting, oil and gas refineries, and water treatment facilities. Common applications include fans, grating tanks, ducts, hoods, pumps, cabinets, and especially in electronic parts. The electrical industry relies on the properties of electrical composite materials for a top performance, unlike parts molded from plastic which can carbonize or melt during exposure to electrical arcing or tracking. During most composite materials experience minimal impact from these common electrical equipment conditions. Composites were more traditionally designed for structural material as compared to composites in structural material. Electronic composites emphasize processing into smaller parts, which leads to lower costs for electrical composite materials. Applications in the electrical industry. The unique properties of the most composites make the material ideally suited to the rigors of use in electrical industry. Phenolic matrix and melamine composites are used in many electronics including printed circuit boards, gears, and insulators. Insulation circuit boards and components requiring a high resistance to heat will often be made from a silicon-based composite. Additional applications include control system components, circuit breakers, arc chutes, arc shields, terminal blocks and boards, substation equipment, microwave antennas, stand-off insulators, pole line hardware, printed wiring boards. Why composite materials? The risk of breakage, underperformance, or failure in an electrical equipment can have devastating safety consequences and significantly impact a company's profits and performance. Electrical equipment requires components that withstand heat and friction and perform reliably over time. These properties are derived from the nature of the composite components. The resin matrix and the reinforcement comprise the major components. The dielectric strength of thermoset component materials has made thermoset composites and go-to material for electrical components. The unique properties is the result of the network of cross-linked molecules that create a rigid structure. Chemical bonds hold the molecule in place. As a result, compounds made with thermoset binders keep their physical and electrical properties under chemical loads during prolonged exposure to elevated temperatures. Characteristics that makes them well suited for electrical use: high thermal conductivity, low thermal expansion, superior electrical insulation, high-low electrical conductivity, electrical magnetic reference (EMI) shielding effectiveness, heat resistance, track resistance, low coefficient thermal expansion, comparative tracking index (CTIU) values exceeding 600 volts.
Where are composite used? Today, thermoset composite are used in a wide range of industries, including aerospace. In aerospace, thermoset composite are being specified for wings, fuselage, bulkheads, and other application in commercial, civilian, and military aerospace application. Appliance and businesses. Thermoset composite are being used in frames, equipment, panels, handles, and trims in appliances, power tools, business equipment, and many other applications. Thermoset composites are for the appliance industry are used in washers, dryers, refrigerators, freezers, ranges, ovens, dishwasher for components that include control panels, handles, knobs, vent trims, side trims, motor housing, kick plates, and many others. Composites are also used in automotive, transportation, farm, construction. Composites are now being used in vehicle and equipment application including panels, frames, interior components, and other parts. Civil infrastructure. Some composite infrastructure applications include buildings, roads, bridges, and pilings. Construction thermoset composites are replacing many traditional materials for home and office architectural components, including fixtures, doors, wall panels, roofing, windows, frame, molding, vanity sinks, shower stalls, and even swimming pools. Corrosive environments. Composites are ideal for application in corrosive environments, such as chemical processing plants, pulp and paper converting, oil and gas refineries, and water treatment facilities. Composites are also used in electrical, with strong dielectric properties including arc and track resistance. Thermoset components include substation equipment, microwave antennas, standoff and pole line hardware, and print wiring boards. Applications and components include switchgear, motor controls, standoff, insulators, control system, components, circuit breakers, arc, chutes, arc shields, terminal blocks, terminal boards, metering devices, bus supports, and lighting components. And in marine, with their corrosion resistance lightweight attributes, marine composite applications include both hulls, bulkheads, and many other components for military, commercial, and recreational boats and ships. What are composites? A composite is a material made from two or more different materials that when combined are stronger than those individual materials by themselves. To simply put, composites are a combination of components in our industry. Composites are materials made by combining two or more natural or artificial elements with different physical or chemical properties that are stronger as a team than as an individual players. The component materials don't completely blend or lose their individual identities. They combine and contribute their most useful traits to improve the outcome or final product. Composites are typically designed with a particular use in mind, such as added strength, efficiency, or durability. Electrical and electronics application of polymers and composites. The emergence of the electrical and electronics industry and the emergence of polymers as a new class of materials are both modern phenomena. The electric relay, a remote switch controlled by electricity that was invented in 1835, was the first electronic device. Bakelite, a thermosetting phenol formaldehyde resin that was developed in 1907, was the first completely synthetic polymer. Hence the electrical and electronics industry and the plastics industry have grown contemporaneously for just a little over a century. Thermoplastic and thermoset. Polymers and their composites are used increasingly more frequently today in a wide range of electrical and electronics applications to perform many different functions. The main reason for this trend is the amazing versatility of polymers, which enable the design and manufacture of vast range of products to meet a very different application requirements at acceptable cost. And the abilities to prepare blends of polymer, to incorporate many types of performance-enhancing additives, and to prepare polymer matrix composite by incorporating reinforcing agents such as fibers, platifillers, and particular fillers, all enhance the versatility of polymers far beyond the versatility of provided by individual polymers on their own. And there are three very broad areas of polymers and composite materials used in electrical and electronics application. Different sets of properties are the greatest importance in each of these three areas of use. Some properties are considered to be important in all use areas. The properties will therefore be discussed under the following four subheadings: electrically insulating polymers, syncally conducting polymers, adhesive coatings, potting, compounds, and sealants, all polymers. Applications of extensive composites are quite extensive, covering computers, appliances, generators, and transformers. To name a few depending on their physical functions, one can categorize them into several types: housing, insulator, resistor, and a conductor. It is to be noted here that the housing material can be an insulator, a conductor, or an electromagnetic wave absorber depending on the specific application.
Advantages and disadvantages of composites. Composites advantages. For some who is accustomed to working with more traditional materials, why might they want to consider composites for their applications? The most common answer is lightweighting. Certainly, composites offer superior strength and stiffness to weight ratios over metals. Corrosion resistance is another common advantage touted by composites manufacturers. And while there are other environmental concerns with composites, such as sensitivity to temperature and moisture, it is true that composites simply don't rust like metals. But there are other unique characteristics of composites that can be attractive to be part or structure designer. For example, composites are typically manufactured in laminate form, meaning the plate or tube or other part is built up by stacking or laminating multiple layers of thin fiber reinforced polymer resin. In each layer, the fibers can be oriented in a direction optimized to carry stress. Careful design of the plate stack-up can provide tailored mechanical properties that are superior to isotropic materials. Isotropic materials means materials that act in same direction. Another lesser known advantages of composites is that they are very damage tolerant as opposed to metal that may fail due to indentation and growth of a single crack. Well-designed composites typically fail due to slow accumulation of many microscopic damage mechanisms. Fibers tend to blunt propagating cracks, so by having fibers running in multiple directions, slow-growing cracks are either stopped or forced to change direction, whether loaded to failure in monatomic matter or loaded cyclical over millions of cycles. The evolution of damage may consist of matrix cracks, fiber matrix debonding, fiber fractures, and delaminations. The result is loss of stiffness of modulus over time, and in some stiffness control applications, the designer must account for the change in stiffness. In doing so, the resulting factor of safety on strength is often very high. This damage tolerance can also change the shape of fatigue life curve, which may have implications for design or test programs as well. Composites challenges. Of course, with these advantages come some challenges as well as the improvement in fatigue performance may be accompanied by greater scatter in fatigue life and strength, requiring more conservatism in design allowables. Composites are also sensitive to notches and holes, and they are typically weak in the thickness direction due to the absence of fibers. Consequently, connections such as bolted or clamped, clamp, clamped joint require careful consideration to avoiding crushing. And due to complex fiber architecture, stress analysis and design are generally more difficult, such that analysis and designers benefit from formal training in mechanics of composites, finite elements, fracture mechanics, polymer engineering, adhesion science, and chemistry. Consulting an experienced composite engineer or development firm is highly recommended to ensure success of metal to composites conversion. As another sources of advantages of composites is advantages of composites: material high strength stiffness, low weight ratio, material can be designed in additional structure, car manufacturer structure eliminate joints. And these are the disadvantages of composites. Composites are heterogeneous, and properties on composites vary from point to point in material. Most engineering structural materials are homogeneous. Composites are highly anisotropic. The strength in composite vary as a direction along which measure changes. Most structural material are isotropic. As a result, all other properties such as stiffness, thermal expansion, thermal electrical conductivity, and the resistance are also ratio anisotropic. The relationship between stress and strain is much more complicated than in isotropic materials.
What composite materials are being used in the field of electronics engineering? Phenolic matrix and melamine composite are being used in the electronics engineering. Phenolic and melamine are thermosetting adhesives that form strong bonds and have good resistance to high temperatures. As thermoset materials, they require heat and pressure to cure and to form a secure bond. Phenolic resins are fairly low in cost. These extremely durable resins are made from chemicals at the phenol group. Typically, phenolic resins are supplied in liquid, powder, and filled form. One of the major contributions of phenolic resins is their use as a matrix in fiber-reinforced composites to prepare materials with low fire smoke toxicity coupled with favorable economics and excellent properties. Phenolics are made of alternating layers of resin and materials, usually cloth, paper, or glass-based fabric. Melamine resins are made through a reaction of diamide with formaldehyde. Most of the resins in this group have excellent dielectric properties. Melamines have a lower molecular weight and are water-soluble, making them useful for laminating or impregnating objects made of other compounds, including paper or board. Melamine resin impregnated composites are frequently used in furniture and flooring. Melamine resins can also be used to make plastics. Phenolic matrix and melamine composites are used in many electronics, including printed circuit boards, gears, and insulators. Insulation circuits, boards, and composites requiring a high resistance to heat will often be made from a silicon-based composite. Additional applications include control system components, circuit breakers, arc chutes, arc shields, terminal block and boards, substation equipment, microwave antennas, standoff insulators, pull line hardware, printed wiring boards, switchgear, panel boards, server rooms, metering devices, lightning components. The reason why they use this composite is because of its strength and heat resistance. The risk of breakage, underperformance, or failure in electrical equipment can have devastating safety consequences and significantly impact a company's profits and performance. Electrical equipment requires components that withstand heat, add friction, and perform reliably over time. These properties are derived from the nature of the composite's components. The dielectric strength and thermoset components materials has made thermoset composites the go-to material for electrical components. The unique property is the result of a network of cross-linked molecules that create a rigid structure. Chemical bonds hold the molecules in place. As a result, compounds made with thermoset binders keep their physical and electrical properties under mechanical loads during prolonged exposure to elevated temperatures. Electronic composites have been used extensively for electronic packaging materials, which often have conflicting requirements that are difficult to meet. High thermal conductivity, low electrical conductivity, and low coefficient of thermal expansion. In addition, low density and low cost are normally required, particularly for commercial packaging and applications. Thus, polymer matrix composites are the most popular choice, while some military and space applications require the use of high performance electronics composites, thus sometimes justifying the use of metal matrix composites and ceramic matrix composites. Application of electronic composites are quite extensive, covering computers, appliances, generators, and transformers. To name a few, depending on their physical functions, one can categorize them into several types: housing, insulator, resistor, and conductor. It is to be noted here that the housing material can be an insulator, a conductor, or an electromagnetic wave absorber, depending on the specific application.